Yeah. So here we have a question on trends of ionization energy. Let's read the statement first. The correct order of increasing ionization energy for the given species is, okay. So you have four species, you have argon, you have P3 minus, you have S2 minus and Cl minus. Okay. These are the four species that you need to compare. Okay. Okay. So there are many factors that are going to play. See, if you can figure out the size, the smaller the size, the more will be the what is basically ionization energy. Ionization energy is the amount of energy required to remove outermost electron from a species, right? 1 mole of species you can say, or gaseous isolated species you can say. All these things are there, but in this case, what we have to keep in mind is either you can calculate this trend using the size. If you know, if the size is small for a species, then electron removal will become difficult. This is one factor. Another factor that is going to play is the inter-electronic repulsion. If there is high inter-electronic repulsion in between the electrons, then electron is going to eject out easily. The third and the most important factor, I'll jot down each and everything, don't worry. The third and the most important factor is the nuclear pull. If nuclear pull is high on the outermost electron, it is going to be difficult to remove that electron, right? Okay. So what I can see is all of them are isoelectronic species. They're isoelectronic. How? I'll explain this. See, you have phosphorus, P3 minus. You have S minus 2. You have Cl minus and argon. You know the atomic number of phosphorus is 15 and you have 3 minus charge. So you'll have 18 electron. Sulfur 16 plus 2 minus charge, 18 electron. Chlorine again 17 plus 1, 18 electron. And argon is, of course, we have 18 electron. If you look at the nuclear charge, phosphorus we have 15 protons, sulfur 16 protons, chlorine we have 17 protons, and argon we have 18 protons, right? So if you compare P3 minus with argon, then you'll observe that in argon 18 protons are going to pull 18 electrons, right? That means in the nucleus of argon you have 18 plus charge. So the nuclear pull on the outermost electron is going to be highest in case of argon. So ionization energy of argon is going to be maximum, right? If you observe P3 minus, 15 protons are going to pull the electrons. So 15 proton in our case is the least number. So if nuclear pull is less, then outermost electron will feel less charge, less attraction, and it is going to be easy to remove that electron. So phosphorus 3 minus will have least ionization energy. Now you can easily observe the trend. This will be P3 minus, then S minus 2, then Cl minus, and then argon. This is going to be the trend. So if you observe in the options carefully, option C is matching with what we have calculated. So option C is going to be the correct answer to this question. Thank you. Yeah, so here we have a sweet and simple question. Let's do it with patience. Which of the following is true? And you have four options. There is bond order, bond length, and bond energy. You have to figure out the relation of proportionality in between these three, right? Let's compare one by one. Okay. So if you talk about bond order, what is bond order? Bond order is basically the number of bonds between two particular atoms. That is what is bond order. Okay. Bond length, the length of the bond in between the atoms. And bond energy. What is bond energy basically? The energy required to break that particular bond or energy lost when that particular bond is found. This is what the bond energy is. These are the general definitions, right? Not going into the particularity or technicality of the definitions. So how you gonna compare bond order with bond length? Let's do it one by one. Okay. See, I'll give you an example. Let's suppose we have AA single bond, right? We have AA double bond, and we have AA triple bond, right? Now I have drawn them in a particular fashion, keeping the bond length and the bond order in mind, right? See, if bond order is going to increase in between two atoms, you take the example of carbon. Carbon single bond, it is longer. When it is double bond, now they are strongly attached to each other, strongly bonded. So they come closer when as compared to the single bond. And when it is carbon-carbon triple bond or for example, AA triple bond, then they are more strongly attracted, more strongly bonded, then they come more closer to each other. That means as you are increasing the bond order, the bond length is decreasing. Bond length is decreasing. That means bond order is inversely proportional to bond length. Look for the option. One can be the answer. Bond order directly proportional to bond length? No. Inversely, yes, it can be. No. So B and D cannot be the answer. Answer is either A or C. Now the next relation is bond order and bond energy. See, when two atoms are closely bonded, when they are close to each other, then it is difficult to break the bond, to break the attraction in between them. That means when bond order is high, bond length is less, bond energy is going to be high. So bond order is directly proportional to bond energy. Should I explain it once more? Okay. See, when the atoms are close to each other, when they have multiple bonds, when bond order is high, that means they're strongly attached, they're strongly bonded. You need more energy to break it. That means if bond order is high, then bond energy is going to be high. I hope now this makes sense to you. So bond order is directly proportional to bond energy. Look for the option. Either it be A or C. In C it is bond order inversely proportional to bond energy. So C cannot be your answer. So the only option left is option A, which says bond order is inversely proportional to bond length and directly proportional to bond energy, what we have observed here. So option A is going to be the correct answer to this question. Thank you. Yeah, so here we have a question on polarizability. Let's read the statement first. Select the correct statements. Okay. Polarizability of these species are compared in these four statements. And then you have option A, B, C and D. You have to figure out which of the comparison is correct, right? Okay. See, let's try and understand what basically polarizability is. Polarizability is the tendency to get polarized. It is the ability of a species to get polarized, right? It is basically the distortion of the electron cloud. Okay. So, for the matter of fact, polarizability, it depends on two fundamental factors. That is, first is size. See, if size is large, polarizability is going to be higher. It will be easily polarized. So, polarizability is directly proportional to size. This is one thing. The another factor is charge. Let me write it. Now, if you have a higher charge, then obviously the tendency to get polarized, tendency of the electron cloud to get distorted is going to be higher, right? So, we have two factors, size and charge, and out of these two, charge is going to be the dominant factor. Let me put 2 star marks over here just to keep that in mind, that charge is the more dominant factor. Okay. Now, let's compare them one by one. You have polarizability of S2 minus is lesser than Se2 minus. Okay. See, you have oxygen, you have sulfur, you have selenium, right? This is where selenium is. Okay. So, if you observe, as you move down the group, size increases, right? The charge is same. So, we cannot compare on the basis of charge. We have to look for size. As you move down the group, the size increases down the group. So, Se2 minus will have higher size than S2 minus. If charge is higher, then Se2 minus is going to have higher polarizability. So, it says S2 minus is lesser. Polarizability of S2 minus is lesser than Se2 minus. True statement. This is true. Let's move on to the second statement. Polarizability of S2 minus is higher than Cl minus. See, polarizability directly depends on charge and size. And which one is the dominant factor? Charge. And here you can clearly see that sulfide has 2 minus charge and chloride has 1 minus charge. So higher charge, higher polarizability. So S2 minus will have higher polarizability as compared to Cl minus. Perfect. This is also true. Move on to the third statement. Polarizability of S2 minus is lesser than P3 minus. Again, P3 minus has 3 minus charge, S2 minus has 2 minus charge. And polarizability is directly proportional to charge. Higher the charge, higher the polarizability. So P3 minus will have higher polarizability than S2 minus, or you can say S2 minus will have lesser polarizability than P3 minus. This statement is also true. Okay. The fourth one is left. If you look at the options, 1, 2, 3, 4 is not there in the option. So 1, 2, 3 correct. So option A might be the probable answer, but let's check for fourth statement also. Polarizability of O2 minus is higher than S2 minus. See, size you have compared, charge is same for O2 minus and S2 minus, size is same. Sorry, the charge is same. The only factor is size, and S2 minus has a bigger size. So it will have higher polarizability, but it says O2 minus has higher polarizability than S2 minus. Incorrect. So this is not correct. So the only correct statements are 1, 2 and 3, and the correct option will be option A, which is going to be the right answer to this question. Thank you. So here we have a numerical from states of matter. Let's read the statement first. 820 ml nitrogen gas was collected over liquid water at 300 Kelvin, 1 atm. Okay. If the vapor pressure of water is 30 torr, okay, then number of moles of nitrogen gas in the moist gas mixture is fine. Okay. So see, you have to calculate the number of moles. We can use PV is equal to nRT, right? The ideal gas equation will assume nitrogen to be an ideal gas. And if you have pressure terms given, you have the volume given to you, and you have temperature also, right? So this is a pretty simple question. Let's see. See, the total pressure given to you is 1 atm. Can I say this total pressure will contain the sum of the pressure of nitrogen and water vapors, right? So I can write it as Pn2 plus P water vapors, right? Okay. So for water vapor, you are given 30 torr, but here the unit is 1 atm. So let's convert that. 1 atm is 760 torr is equal to P nitrogen plus 30 torr. From here I can calculate pressure of nitrogen gas is going to be 760 minus 30, that is 730 torr. Makes sense, right? Okay. Now you need to calculate moles of nitrogen. Can I say PV is equal to nRT? So from here N will be PV by RT, right? So moles of nitrogen will be pressure of nitrogen into volume of nitrogen upon R into T. Okay. Value of R has to be taken care of. So pressure of nitrogen is 730. Let me convert into atm so that I can easily put R in liter atm, right? Okay. So I have to convert volume of nitrogen into liter, that is 821 by 1000 liter, and pressure of nitrogen into atm, that is 730 by 760 atm, right? Let me put these values. 730 by 760 into, this will be 0.821, 821 divided by 1000 divided by the value of R. Okay, 0.0821. Some simple calculations, some cancellation will be done, and temperature is given as 300 Kelvin, right? Okay. If you solve this, it will be like this 821 cancelled with 821 with 10 over here, and this 10 gets cancelled with this 0 with 0. What you are left with is, let me write it here, 73 by 76 into 1 by 30, right? Okay. So if you just look at the options, they are far apart. I can take some sort of approximation. 73 by 76 is somewhere around 0.9 and 0.96 into 1 by 30, right? So this is what? 0.096 by 3. So if you calculate 0.096 by 3, it will be 0.032. Right, 0.032. Okay, let's look for the option. See, option B is clearly there. 0.032 is exactly matching with what we have calculated. So option B is going to be the right answer to this question. Thank you. So here we have a question on enthalpy of formation, a very beautiful question. Let's see what the question says. In the reaction, and there's a reaction given to you, CS2 liquid reacting with oxygen gas, and then it is forming CO2 gas and SO2 gas. The delta H for the reaction is minus 265 kilocalorie. Okay. The enthalpy of formation of CO2 and SO2 are both negative and are in the ratio 4:3. Okay. The enthalpy of formation of CS2 is plus 26 kilocalorie per mole. Fine. This is the data given, and we have to calculate the enthalpy of formation of SO2, and the unit is kilocalorie per mole. Perfect. And you have 4 options, all the negative values. Fine. So let's see how we're going to do this. Let's first interpret this 4:3 ratio, right? CO2 is to SO2. So can I say that delta H formation of CO2, can I assume it to be, and delta H formation of SO2, both gases, they are in the ratio 4:3 with the negative values. So can I assume it to be minus 4x and minus 3x kilocalorie per mole? Right? I hope this makes sense. Perfect. And the reaction is CS2 reacting with oxygen to form CO2 and SO2. Right? Perfect. CS2 is in liquid state, oxygen is in gaseous state, CO2 is in gaseous state, and SO2 is also in gaseous state. Perfect. If you just balance this reaction, you have 2 sulfur on the reactant side. So you will write 2 here to balance it. And now you have 6 oxygen atoms on the product side. So I'll write 3 over here. Now the reaction seems to be balanced. Let's write the enthalpy of reaction in terms of enthalpy of reaction in terms of formation, enthalpy of formation, right? So it will be summation of enthalpy of formation of product minus summation of enthalpy of formation of reactant. Okay. What do you have on the product side? You have CO2, so delta H formation of CO2 plus 2 into delta H formation of SO2. Right, this is your product. Okay, and if you write the reactant side, this will be like minus delta H formation of CS2 liquid plus 3 into delta H formation of oxygen gas. Right, and you have CO2 gas here, SO2 gas here. Perfect. Now you have some values given. The delta H of the reaction is given to be what? I'll write it here. It is minus 265 kilocalorie. Everywhere the unit is kilocalorie, so no need to worry about that. Delta H formation of CO2, we have assumed it to be minus 4x. Right? Delta H formation of SO2, it is minus 3x, and because it is twice, so twice of minus 3x. Right? This is for the product part. Let's write for the reactant part, minus delta H formation of CS2. The value is given to you in the equation. It is plus 26 kilocalorie per mole. Okay. So this will be like 26 plus 3 into delta H formation of O2, oxygen gas. Now this value is neither given nor we have assumed. So how are you going to write it? Remember one thing, that delta H formation of a standard elemental state is assumed to be 0, and for oxygen, O2 gaseous state is its standard elemental state, so this value is going to be 0, right? So no need to worry about it. 3 into 0 is 0. Now if you solve this, minus 265 plus 26, okay, minus 265 plus 26 and minus 4x, 3 into 2 minus 6x, this is going to be minus 10x. Now if you solve this, This will be like what? 265, 26, 25 will be 40, 26, 239. Minus 239 is minus 10x, and x is going to be what? 23.9 kilocalorie, right? So is it going to be the final answer? Answer is no. You have to calculate enthalpy of formation of SO2, right? So this is what is required in the question. So delta H formation of SO2 gas is what we have assumed it to be minus 3x, right? And the value of x is coming out to be what? 23.9. Perfect. 23.9. If you just multiply 9 into 3 is 27, 2, 3, 3, 9, 11, 3, 2, 6, 7. Minus 71.7 kilocalorie per mole is going to be your final answer. Let's match with the options. And option D exactly matching with what you have calculated. And with that, I rest my pen. Thank you.